One of the most enduring ideas in all the universe is that everything that exists now will someday come to an end. The stars, galaxies, and even the black holes that occupy the space in our universe will all someday burn out, fade away, and otherwise decay, leaving what we call a heat death. But perhaps there are exceptions to this general rule, and some things will truly live on forever. One such thing is the photon. All of the electromagnetic radiation that exists in the universe is made up of photons, and photons, as far as we can tell, have an infinite lifetime. Does that mean that light will truly live forever? It's not necessarily an easy question to answer. We can fathom circumstances where they might decay, convert into other particles, or undergo unexpected changes. In the 1910s, Vesto Slipher was working at the Lowell Observatory in Flagstaff, Arizona. During this time, he focused on observing what were then called spiral nebulae, which we now know as galaxies. Slipher used spectroscopy to study the light from these distant objects. This technique allowed him to analyze the spectrum of light emitted by these nebulae. In 1912, Slipher discovered that most of the spiral nebulae he observed were moving away from Earth at high speeds. This was evident from the redshift in their spectra, indicating that the light waves were stretched as the objects moved away. As the fundamental particle of light in all forms of electromagnetic radiation, photons play a major role in the universe. But are they truly the only stable particles in existence? To answer this question, we must first understand what we mean by stability in the context of particle physics. A stable particle is one that does not decay into other particles over time. In contrast, unstable particles have a finite lifetime before they transform into other, more stable forms of matter or energy. Photons, indeed, are considered fundamentally stable. They have no rest mass, travel at the speed of light, and do not decay spontaneously. This stability is a cornerstone of our understanding of the universe, as it allows light to traverse vast cosmic distances, bringing us information from the farthest reaches of space and the earliest moments of the Big Bang. However, photons are not alone in their stability. The electron, another fundamental particle, is also considered stable. Despite being much different from photons, having mass and electric charge, electrons have never been observed to decay. Protons, the positively charged particles found in atomic nuclei, are also remarkably stable. While theories predict that protons might decay over extremely long timescales, this has never been observed experimentally. For all practical purposes, protons are considered stable, which is fortunate as their decay would lead to the disintegration of atomic nuclei and the collapse of matter as we know it. Neutrinos, ghostly particles that interact weakly with other matter, are another candidate for stability. While neutrinos come in different flavors that can oscillate between forms, they are not thought to decay into other particles. It's worth noting that the stability of these particles is fundamental to the structure and evolution of our universe. If photons were unstable, the cosmos would be dark, and information could not propagate across space. If electrons or protons decayed rapidly, matter would disintegrate, and stars and galaxies could not form. What evidence do we have that photons are eternally stable? Photons are thought to be stable due to conservation laws, particularly the conservation of electric charge. Since photons are electrically neutral, they cannot decay into charged particles without violating this fundamental principle. Einstein's theory requires that photons always travel at the speed of light in vacuum. This implies they experience no proper time, making decay impossible from their perspective. Light from distant galaxies in the cosmic microwave background has traveled for billions of years to reach us. If photons were unstable, we would expect a significant portion of this light to have decayed during its journey. However, observations match predictions assuming photon stability. Scientists have conducted precise measurements of photon properties in controlled settings. No evidence of photon decay has been observed in these experiments. One of the most fascinating aspects of photons is their ability, under certain circumstances, to transform into other particles. This process, known as transmutation, is governed by the laws of quantum mechanics and is subject to various conservation principles, including the conservation of energy, momentum, and charge. The most common forms of photon transmutation involve the creation of particle-antiparticle pairs. One of the most well-known examples of photon transmutation is pair production. In this process, a high-energy photon can spontaneously convert into an electron-positron pair when it interacts with the electric field of an atomic nucleus. This phenomenon occurs only when the photon's energy exceeds the combined rest mass energy of the electron and positron. While photons do not typically interact with each other in classical physics, quantum electrodynamics predicts that high-energy photons can indeed collide and produce particle-antiparticle pairs. This process becomes significant in extreme environments, such as near neutron stars or in the early universe. Recent experiments at the Large Hadron Collider have provided evidence for light-by-light scattering, a phenomenon where photons effectively bounce off each other, hinting at the possibility of more complex photon-photon interactions. In the presence of strong magnetic fields, such as those found near magnetars, a single photon can split into multiple lower-energy photons. This process, known as photon splitting, is a direct consequence of quantum electrodynamics and demonstrates the malleability of photons under extreme conditions. Quantum field theory introduces the concept of virtual particles, which can briefly pop into existence due to quantum fluctuations. Photons can temporarily transmute into these virtual particle-antiparticle pairs, which quickly annihilate back into photons. This process, while not directly observable, plays an important role in many quantum phenomena and contributes to effects like the Lamb shift in atomic spectra. Under certain conditions, photons can even transmute into hadrons. This process, known as vector meson dominance, occurs when a high-energy photon fluctuates into a quark-antiquark pair, which then forms a vector meson. This phenomenon is particularly important in understanding certain aspects of high-energy particle physics and the strong nuclear force. The universe has been expanding since the Big Bang, approximately 13.8 billion years ago. This expansion is not like an explosion from a central point. Rather, it is the stretching of space itself. Galaxies are moving away from each other as space expands, and the farther away a galaxy is, the faster it appears to be receding. This phenomenon is described by Hubble's law, which states that the recessional velocity of a galaxy is proportional to its distance from us. This cosmic expansion has a direct effect on photons, which travel through space at the speed of light. As space stretches, so too does the wavelength of these photons. This process is known as cosmological redshift. Photons are characterized by their wavelength, which determines their energy and the type of electromagnetic radiation they represent. When a photon is emitted from a distant galaxy, it begins its journey across the expanding universe. As it travels through space, the expansion of the universe stretches the space through which the photon moves, and consequently, the photon's wavelength is also stretched. This stretching of wavelength results in a redshift, a shift towards the red end of the electromagnetic spectrum, where wavelengths are longer. This redshift is not due to the Doppler effect, which is the change in frequency of a wave in relation to an observer moving relative to the wave source, but rather a result of the expanding universe itself. The amount of redshift a photon experiences is proportional to the amount of expansion that has occurred during its journey. The greater the redshift, the more the universe has expanded, and the longer the photon has been traveling. The energy of a photon is inversely proportional to its wavelength. As the wavelength of a photon increases due to the cosmological redshift, its energy decreases. This phenomenon is often referred to as photon fatigue or tired light. We will take tired light later on this video. As the universe expands, the wavelength of each photon traveling through space stretches, leading to a decrease in its energy. The longer the photon travels, the more it redshifts, resulting in progressively lower energy levels. Given enough time, this redshift will continue indefinitely, causing the photon's energy to approach zero asymptotically. In the far future, if the universe continues to expand at an accelerating rate, as current observations suggest, photons will continue to redshift until they become undetectable. This scenario is sometimes referred to as the heat death of the universe, where all energy sources, like stars, have burned out, and the remaining photons are so stretched that they carry almost no energy. In practical terms, photons will continue to redshift beyond the point where they can interact meaningfully with matter or be detected by current instruments, making them effectively invisible as their energy levels become exceedingly low. This process highlights the inextricable link between the universe's expansion and the fate of photons within it. Does the creation of new photons due to dark energy ensure a finite and positive photon number density at all times? No, the creation of new photons due to dark energy does not ensure a finite and positive photon number density at all times. The standard cosmological model, which includes dark energy as a cosmological constant, does not predict the creation of new photons as a direct result of dark energy. Instead, as the universe expands, the number density of photons decreases because the photons are spread out over an increasing volume of space. This dilution effect means that the photon number density decreases over time, even though the total number of photons remains constant. In alternative cosmological theories, where dark energy or other exotic fields might lead to the creation of new photons, the situation could be different. However, these theories are speculative and not supported by current observational evidence. In the standard model, as the universe expands, the photon number density will continue to decrease, approaching zero in the far future, although it will never actually reach zero within a finite time. This means that while the universe will always contain some photons, their density will become exceedingly low, especially as the expansion of the universe continues to accelerate. Thus, the creation of new photons, if it were to occur, would need to be on a scale sufficient to counteract the dilution caused by the expansion, which is not the case in current models. In particle physics, the lifetime of a particle typically refers to the time it takes for the particle to decay into other particles. Photons, as massless particles, are unique in that they do not decay into other particles under normal circumstances. In this sense, they can indeed be considered to have an infinite lifetime. They persist indefinitely, traveling through space without undergoing any intrinsic decay process. The idea of an infinite lifetime seems paradoxical when paired with the concept of continuous energy loss. In one sense, the photon persists forever, but in another, its ability to interact with matter and exert influence diminishes as its energy decreases. If we consider the photon's lifetime purely in terms of its existence, then it can indeed be considered to have an infinite lifetime. However, if we consider its lifetime in terms of its ability to interact with its environment or to carry meaningful amounts of energy, the situation becomes more nuanced. As the universe continues to expand, photons redshift to lower and lower energies, eventually reaching a state where their energy is so low that they are practically undetectable and have minimal interaction with matter. In this scenario, although the photon technically still exists, it has lost most of its physical significance. Is the absorption and re-emission of a photon by an atom considered the death of the original photon? Photons are quantum particles of light that carry energy proportional to their frequency. When a photon encounters an atom, it can be absorbed by an electron within the atom if the photon's energy matches the energy difference between two electron energy levels. This process excites the electron, causing it to jump to a higher energy level. The photon effectively ceases to exist in its original form at the moment of absorption, as its energy is transferred to the electron. After a brief period, the excited electron may return to a lower energy level, emitting a new photon in the process. This new photon carries energy equal to the difference in energy levels between the excited and lower states. The emitted photon may have the same energy as the absorbed one, but it may also differ in direction, phase, polarization, and even wavelength, depending on the specifics of the atomic transition and external factors like magnetic or electric fields. The idea of death in the context of quantum mechanics is not straightforward. In classical physics, an object or particle is said to die if it undergoes a fundamental transformation that results in its cessation as a distinct entity. However, quantum particles like photons do not adhere to classical notions of identity. The identity of a photon is not tied to any intrinsic property that persists through its interactions with matter. When a photon is absorbed by an atom, it loses its distinct identity as a photon. The energy that once defined it is now part of the atom's internal energy. From a quantum mechanical perspective, the photon has undergone a transition into a different state, namely the excited state of the atom. If we consider the original photon to be defined by its energy, frequency, and momentum, then its absorption marks the end of its existence as a discrete quantum of light. The re-emission process is often thought of as the birth of a new photon. The newly emitted photon, while possibly similar in energy and frequency to the absorbed photon, is not the same photon. It may have different properties such as direction or polarization, and it is generated as a result of the atom's transition back to a lower energy state. This process of absorption and re-emission can be seen as analogous to the cycle of life and death in biological systems, where one entity ceases to exist, and a new one emerges from the remnants of the old. In this analogy, the absorbed photon dies, and a new photon is born from the atom's transition. The connection between the absorbed photon and the emitted photon is indirect, mediated by the atom's internal energy states. From a philosophical standpoint, the question of whether the original photon dies hinges on how we define identity in the quantum realm. In classical physics, identity is often tied to continuity and persistence of intrinsic properties. However, in quantum mechanics, particles like photons are defined more by their quantum states than by any persistent intrinsic identity. If we adopt a view that ties identity to continuity of existence and properties, then the absorption of a photon by an atom could indeed be considered the death of that photon. The original photon, with its specific energy, frequency, and momentum, no longer exists in that form once it is absorbed. The energy has been transferred to the atom, and any subsequent photon emitted by the atom is a new entity, not a continuation of the original photon. However, if we consider the identity of a photon to be tied to the broader quantum field from which it emerged, then the concept of death becomes less clear-cut. In this view, the absorption of a photon is simply a transition of energy within the quantum field, and the re-emission of a photon is another manifestation of that energy. The death of the original photon is less a cessation of existence and more a transformation within the continuous underlying quantum field. How does the passage of a photon through material affect its speed and energy? In a vacuum, photons travel at the speed of light, denoted as c, which is approximately 299,792 kilometers per second. However, when photons pass through a material medium such as glass, water, or air, they appear to slow down. This apparent reduction in speed is due to the way photons interact with the atoms in the material. Photons do not directly slow down in the sense that they lose speed. Rather, they are absorbed and re-emitted by the atoms in the material. This process of absorption and re-emission takes a finite amount of time, causing a delay in the photon's overall progress through the material. The result is an effective speed of light in the material that is less than c. This reduced speed is characterized by the material's refractive index, which is defined as the ratio of the speed of light in a vacuum to the speed of light in the material. However, when photons interact with the atomic structure of the material, they can experience various effects that might alter their apparent energy. One such effect is scattering, where photons are deflected by atoms or molecules, potentially changing their direction without altering their energy. Another effect is absorption, where photons may be absorbed by the material, transferring their energy to the atoms and causing electron excitations. In this case, the original photon ceases to exist, and its energy is converted into other forms, such as heat or the energy of an excited electron. In transparent materials, where photons primarily pass through without being absorbed, their energy remains consistent, but their speed is effectively reduced due to the repeated absorption and re-emission process. The photon's wavelength may also change when they enter a material with a different refractive index, while their frequency, and thus their energy, stays constant. This change in wavelength does not signify a change in energy, but reflects the photon's adaptation to the new medium's properties. A photon cannot be considered the same particle after it has been absorbed and re-emitted by an atom. The original photon is absorbed, and its energy is transferred to the atom, effectively ending its existence as a distinct quantum entity. The photon that is subsequently emitted is a new particle, even if it shares some of the properties of the original photon. This distinction reflects the broader principle in quantum mechanics that identity is tied to quantum states rather than to the persistence of individual particles. What is the tired light hypothesis, and how does it relate to the longevity of photons? The tired light hypothesis is an alternative explanation to the redshift observed in light from distant galaxies, which challenges the conventional understanding provided by the Big Bang theory. Proposed by Fritz Zwicky in 1929, the tired light hypothesis suggests that the redshift is not due to the expansion of the universe, but rather is a result of photons losing energy as they travel through space. This energy loss, according to the hypothesis, causes the light to shift toward the red end of the spectrum, similar to how an object moving away from an observer causes a Doppler redshift. In the 1920s, the discovery that light from distant galaxies is redshifted led to the development of two major interpretations. The first, which became the foundation of the Big Bang theory, was that the redshift is due to the expansion of the universe. The second was the tired light hypothesis, which sought to explain the redshift without invoking cosmic expansion. Zwicky proposed that as photons travel across vast intergalactic distances, they interact with particles or fields in space, losing a small amount of energy with each interaction. This energy loss would gradually reduce the frequency of the photons, causing their wavelength to increase and shift toward the red end of the spectrum. When light passes through something like space dust, it should slow down differently depending on its color, wavelength. Just like a prism separates colors, this medium should make different colors of light slow down by different amounts. But when we look at light from faraway sources, we don't see this happening. All colors of light are redshifted, stretched, the same amount no matter the distance. This means the first prediction of the tired light idea is wrong. If distant light lost energy by traveling through a medium, distant objects should look blurrier than closer ones. But we don't see that either. Distant galaxies appear just as sharp as nearby ones, which disproves the second prediction. The tired light hypothesis has implications for the longevity of photons, as it suggests that photons do not maintain their energy indefinitely. According to the hypothesis, as photons traverse the cosmos, they gradually lose energy through interactions with the medium or fields they encounter. This energy loss could be interpreted as a kind of aging process for photons, where they lose their initial vibrancy and shift toward the red end of the spectrum over time. However, in the context of the standard model of cosmology, photons are considered to have an indefinite lifespan, as long as they do not interact with matter or other photons in a way that leads to absorption or scattering. In an expanding universe, the redshift of photons is due to the stretching of space itself, not an intrinsic loss of energy by the photons. Therefore, under the Big Bang model, photons can persist for billions of years, traveling across the universe with their energy and wavelength determined by the cosmic expansion. Does the idea that photons do not actually exist, as proposed by some physicists, challenge the concept of their eternal existence? The idea of photons emerged from early 20th century experiments that revealed light behaves both as a wave and as a particle. This duality was encapsulated in the photon concept, with Albert Einstein's explanation of the photoelectric effect, providing strong evidence for the existence of photons. When light shines on a material, it can eject electrons from the surface. The energy of the ejected electrons depends on the frequency of the light, not its intensity, suggesting that light consists of discrete packets of energy, photons. This particle-like behavior of light, combined with its wave-like characteristics, such as interference and diffraction, led to the development of quantum mechanics. In this framework, photons are the quanta of the electromagnetic field, carrying energy proportional to their frequency. Despite the success of the photon model in explaining various phenomena, some physicists argue that photons may not exist as discrete particles. This skepticism stems from the continuous nature of the electromagnetic field in quantum electrodynamics. In quantum electrodynamics, what we perceive as photons are actually excitations of the electromagnetic field, not individual particles. According to this view, the electromagnetic field is a continuous entity, and the energy exchanges we interpret as the emission or absorption of photons are simply changes in the state of this field. This interpretation challenges the concept of photons as fundamental particles. If photons are merely excitations of a field, then they do not exist as independent entities, but are instead manifestations of the underlying field. This view aligns with the idea of field theory, where particles are seen as excitations in their respective fields, rather than as standalone objects. In this context, the concept of eternal existence for photons becomes problematic, because what we call a photon is not a permanent, unchanging particle, but a transient disturbance in the electromagnetic field. If photons do not exist as discrete particles, the idea of their eternal existence must be reconsidered. The traditional view holds that photons, once created, travel through space indefinitely unless they interact with matter. However, if photons are merely excitations of the electromagnetic field, Their existence is tied to the field's state and the conditions of the environment through which they propagate. For example, in a vacuum, the electromagnetic field can support the propagation of disturbances that we interpret as photons. However, these disturbances are not independent objects. They are temporary configurations of the field that can change, dissipate, or be absorbed by matter. This perspective suggests that photons, as we understand them, do not have an eternal existence because they are not permanent entities. Instead, they are temporary states of the electromagnetic field that depend on the surrounding environment. David Bohm's interpretation of quantum mechanics, often referred to as the Bohmian interpretation or pilot wave theory, offers a distinct perspective on the nature of photons and their behavior compared to the more widely accepted Copenhagen interpretation. According to the Copenhagen interpretation, the properties of quantum particles, including photons, do not have definite values until they are measured. This leads to the famous wave-particle duality, where photons exhibit both wave-like and particle-like behaviors depending on the experimental setup. Bohmian mechanics, on the other hand, posits that particles such as photons have well-defined trajectories at all times. These trajectories are determined by both the initial conditions of the system and a guiding wave, known as the pilot wave. This wave is a real physical entity, described by the same wave function that governs the behavior of particles in the standard quantum framework. The key difference lies in the interpretation. While the Copenhagen interpretation sees the wave function as a tool for predicting probabilities, Bohmian mechanics treats it as a guiding field that influences the motion of particles. In the context of Bohmian mechanics, photons are not merely abstract probability distributions or wave packets that collapse upon measurement. Instead, they are considered real particles with definite positions and momenta. The wave function, or pilot wave, associated with a photon influences its path, guiding it through space in a manner that depends on both the initial conditions and the surrounding environment. This interpretation of photons offers a different explanation for phenomena like interference and diffraction. In the Copenhagen interpretation, these effects are explained by the wave-like nature of photons, where each photon can be thought of as existing in a superposition of states until it is observed. In Bohmian mechanics, however, the photon follows a definite path, but its trajectory is influenced by the pilot wave, which interacts with itself in the case of double-slit experiments, creating the interference pattern. Can the claims that photons do not exist or have finite lifetimes be tested experimentally? Photons do not exist, according to Jeff Jones of the University of Sussex. Jones believes that it is wrong and unnecessary to describe light in terms of small, localized particles. If he is right, the quantum world is less mysterious than physicists would have us believe. Jones has used his controversial idea to eliminate some of the confusion surrounding quantum descriptions of the famous double-slit experiment, which demonstrates that light can behave both as a wave and a particle. In the double-slit experiment, a beam of light passes through the two slits and produces an interference pattern on a detector screen, a pattern of light and dark bands. A similar kind of pattern is produced when water waves pass through slits. The puzzle of quantum physics is that even when the beam of light is so weak that it can be considered to be made of particles of light, or photons, the spots of light made by individual photons arriving at the screen eventually build up an interference pattern. How does each photon, which common sense says can only go through one slit or the other, know about the slit it does not go through and direct itself to the appropriate place on the detector screen? Jones quotes many standard texts which highlight this phenomenon, described by Richard Feynman as the central mystery of the quantum world. He then explains that they are all wrong. In his picture, an electromagnetic field fills the entire experiment, in principle, the entire universe, and knows that there are two slits there. What actually travels through the experiment is not a little particle, but a disturbance in the electromagnetic field. What is detected as a photon is the removal of one quantum or packet of energy from the field. The idea of a single photon propagating is meaningless, says Jones. Using a similar argument, Jones previously pointed out that the work for which Einstein received his Nobel Prize, the proof that photons exist based on the photoelectric effect, is similarly flawed. All that is proved is that energy can only be added to or subtracted from the field in definite units. But recently, some researchers have carried out the double-slit experiment using electrons, fired one at a time, to build up an interference pattern. How does Jones explain that? Although he does not discuss this version of the experiment in his paper, he told New Scientist that this is a very interesting problem, which can be tackled in several different ways. He favors the idea that electrons are real particles, and that their statistical distribution after being fired through the two slits depends on a wave associated with the electrons. This echoes an interpretation of quantum mechanics based on the work of David Bohm, long considered a maverick, but whose work is now seen as a serious alternative to the standard Copenhagen interpretation of quantum mechanics. Intriguingly, Jones points out that in this picture, although the interference pattern produced by electrons will look like the interference pattern produced by light to a first approximation, other properties of electrons should produce as eigenorder effects, which are, in principle, measurable, so his claims could be tested. If he is right, all those textbooks that talk about photons as particles will have to be rewritten and many lecture courses revised. If photons truly live forever, what does this suggest about the nature of time and the universe? In the framework of special relativity, photons travel at the speed of light. At this speed, the concept of time as experienced by objects with mass breaks down. For a photon, no time elapses between its emission and absorption, meaning it exists in a state where time, as we understand it, doesn't apply. This timeless existence suggests that at the most fundamental level, time may not be an intrinsic property of the universe, but rather a construct that emerges for objects with mass. If photons do not experience time and can theoretically exist forever, this suggests that the universe itself might have an eternal aspect. While other physical entities might undergo change, decay, or transformation, photons would be constant entities, persisting through all cosmic events, from the birth of the universe to its possible end. The longevity of photons ties into the idea of an expanding universe. As the universe expands, photons stretch and lose energy, redshift, but they continue to exist. This implies that even in a vastly aged universe, photons from the earliest times will still be present, albeit with diminished energy, serving as relics of the universe's distant past. The eternal existence of photons might imply that time is not a fundamental aspect of the universe, but an emergent property linked to the behavior of massive particles. In a universe where photons persist without aging, the concept of time becomes more about relative experiences between massive objects rather than an absolute universal flow. How does the concept of photons living forever relate to the idea of a heat death of the universe? The concept of photons living forever is closely related to the idea of the heat death of the universe, a theoretical scenario in which the universe reaches a state of maximum entropy, and all processes that increase entropy have ceased. The heat death of the universe refers to a state in which all energy is uniformly distributed, and there are no gradients, differences in temperature or energy, left to drive physical processes. In this scenario, the universe would be in thermodynamic equilibrium, with no usable energy to perform work. As the universe evolves, entropy increases, leading to a more disordered state. The heat death represents the final state of maximum entropy, where all structures have decayed and all energy differences have been smoothed out. Photons play a critical role in the energy distribution of the universe. Over time, as stars burn out and other energy sources deplete, the universe becomes increasingly filled with low-energy photons. These photons, produced by processes like the cosmic microwave background, CMB, and the radiation of heat from objects, contribute to the uniformity of energy distribution. As the universe expands, photons are redshifted, meaning their wavelengths stretch and they lose energy. This process cools the universe, contributing to the gradual decline in temperature that is characteristic of the approach toward heat death. If photons live forever, they will continue to exist even as the universe approaches heat death. However, as the universe expands, these photons will become increasingly redshifted, eventually reaching extremely long wavelengths with very low energy. In the heat death scenario, the universe would be dominated by these low-energy, long-wavelength photons. Since no further energy exchanges can occur, the universe would be a cold, dark, and static place, filled with a dilute sea of nearly inert photons. Photons, especially low-energy ones, are significant carriers of entropy. As the universe cools and structures break down, the number of photons increases, spreading the energy more evenly across the cosmos. This distribution of photons contributes to the rise in entropy, pushing the universe toward its maximum entropy state, the heat death. The fact that photons may live forever suggests that they will persist into this state of maximum entropy. However, even though they continue to exist, their ability to contribute to meaningful processes, like energy transfer or work, will have ceased, as they will be in a state of equilibrium. There are exotic scenarios we can cook up that will change the story, of course. Perhaps it's possible that photons really do have a non-zero rest mass, causing them to slow down to slower than the speed of light when enough time passes. Perhaps photons really are inherently unstable, and there's something else that's truly massless, like a combination of gravitons, that they can decay into. And perhaps there's some sort of phase transition that will occur, far into the future, where the photon will reveal its true instability and will decay into a yet unknown quantum state. But if all we have is the photon as we understand it in the standard model, then the photon is truly stable. A universe filled with dark energy ensures, even as the photons that exist today redshift to arbitrarily low energies, that new ones will always get created, leading to a universe with a finite and positive photon number and photon energy density at all times. We can only be certain of the rules to the extent that we've measured them, but unless there's a big piece of the puzzle missing that we simply haven't uncovered yet, we can count on the fact that photons might fade away, but they'll never truly die.